What is a structure function? Let's start from the beginning. Let's take a very simple power package. Here is the die, and at the top of the die is a heated area. Here is the die attach. Die attach is not normally this thick, but I have drawn it like this to make it easier to see. And here we have a copper base. The aim is to find out the temperature here and the quality of the die attach here. Here is how. We heat up the component by applying constant power. Then we start the measurement here at 0. At this point, this area will get to a hot state and the heat will spread in circles. There are two ways to illustrate heat spreading. We can use heat flux vectors, which move from the heated area through the silicon verse, then to the die attach, and then they spread around into the base. The second way is to draw perpendicular lines to the vectors, resulting in circles showing the heat spreading down from the hottest at the top here and decreasing as we move away from the source. These lines denote isothermal surfaces. At the beginning of the measurement, turn the power off and maintain it at a low level. The device will then begin to cool down and the heat will retreat into the heat source and the structure slowly cools down. This can be represented as a temperature versus time curve. You have probably seen cooling curves shown over a linear timescale in the form of an exponential function. For example, this is the way your morning coffee cools down. In the case of a thermal system, we are curious to see the properties of very small package features, such as a die attach, as well as the big ones, like a cold plate. We prefer to show the curve over a logarithmic timescale like this. What is the relationship between this temperature curve and this picture here? This curve can be explained with exponential functions. If we have a simple structure, for example, just a block of uniform copper, how can we describe it? The heat comes from the top. We can describe it with a thermal resistance and a parallel connected thermal capacitance. The thermal resistance will make sure that if we heat it up from this point, the temperature will be different here. So we have T1 and T2. If we have the same temperature graph for this simple example, it will look something like this exponential curve. Here is the equation. Here we have the tau intensity diagram. Tau equals R times C. This basically means that if you have this model here and you know the thermal resistance and the tau value, you can work out the C very easily. We can also show these in a plot where we show the R value over the corresponding tau value. If you have a more complex structure, the same applies, but you just have multiple stages. If we know all the tau values and all the R values, we know the thermal properties of the system. On this curve we have an exponential function here, some smaller ones here and another here. This curve is a sum of many of these exponential curves where the R's and C's are different values. So what we have to do is to try and figure out the R's and C's in the models. Based on this curve, we create a model like this. There is a mathematical way of getting these R and C numbers, so we can give a perfect description of the behaviour of our package. To do this, the Foster model can be transformed into the Cauer model, which carries the same information but can be read as a physical model of the real structure. The elementary heat capacitances are not parallel with the elementary heat resistances. Instead, all refer to the ambient. To recap, we measure this curve, then we break down the curve to a number of R's and C's. Then we do a mathematical transformation from a so-called Foster-type thermal model to a ladder-shaped Cauer model. Once the translation is done and we have these values, the structure can be very easily seen. The thermal resistances are defined between two isotherms, such as a delta T between here and divided by the delta P. The thermal capacitance is proportional to the volume between the two isotherms. For example, if we had a package with a cavity, the thermal resistance will be larger, so the corresponding R's will increase and we will see the changes in the structure function. This is just a network model. How do we get a full structure function out of it? Along this axis is the sum of the capacitances of the ladder model, and along the bottom is the sum of the resistances. The heat propagates from here, then goes into a resistance and some capacitance, so the curve starts to go up. Then there is more resistance and capacitance, so the curve goes up again. When the heat is going through the first part of the system, which is the die itself, There is not much resistance, so the curve here is steep. When we move into the die attach, which is very small so it doesn't store too much heat, but the thermal resistance is bigger, especially with the cavity there, we start to add more resistance. R is big, so the line flattens out. The length of this part of the curve will be in direct relationship with the size of the cavity in the die attach. The heat eventually goes into the less resistive copper base, which is shown by this steep part of the curve. If there is additional thermal interface material after, the curve will flatten out, then go steep again as you hit a cold plate. Then the whole thing will cool down and go into infinite capacitance. If something goes wrong, for example if the grease is bad, it will show up with a longer curve like this, and the function will go to the infinity further along. Or if the die attach is wrong, then this curve will be longer and again shifts the functions further along the graph. So, in summary, we start with this picture, then we cool it down, and based on the speed that the heat goes back, we get this bumpy curve. From this curve we can derive the R and C values, as these are all exponential functions. We can get this Foster model, which can then be transformed into the ladder model, which is a direct physical description of the first image. And then we plot some of the resistances and capacitances. If something is very resistive, they will usually show as the flat part of the curve. Something that is capacitive, usually structure or metal, is shown in the steeper parts of the curve. Thank you for watching this introductory video to structure functions. Why not explore our website now, where there are many more resources that will help you to further understand this topic and learn how to use this knowledge to simulate accurate thermal models.